A rare visitor from deep space is flying through our solar system. The object, now officially named 3Y Atlas, has astronomers spotting another mysterious interstellar visitor racing through space. NASA's recent data has revealed anomalous features that have sparked intense debate over its true nature. Some scientists fear the possibilities this mysterious visitor presents, suggesting it could be more than a mere comet or asteroid, perhaps even a disguised alien ship. This revelation has generated both excitement and apprehension within the scientific community as we strive to understand its origin and purpose. The breaking discovery. The initial detection of 3Y Atlas occurred in early 2025 by the Atlas Survey System, an automated telescope array designed to spot near-Earth and interstellar objects. Astronomers were immediately intrigued by the object's extraordinary velocity and hyperbolic trajectory that clearly indicated it was not gravitationally bound to our solar system. Dr. Larry Deneau, lead scientist for the Atlas project, confirmed the object's unique path and immediately alerted observatories worldwide to begin tracking this unprecedented visitor. The breaking revelation that 3I Atlas was significantly larger and faster than previous interstellar objects reignited debates about the prevalence of such cosmic travelers. The discovery highlighted the increasing sensitivity of modern astronomical detection tools and emphasized the critical importance of global coordination in tracking these extraordinarily rare cosmic interlopers. Initial observations revealed unusual characteristics that defied conventional explanations for natural interstellar objects. The object's behavior patterns suggested it might possess properties unlike anything previously encountered in our solar system. This discovery marked a pivotal moment in interstellar object research, forcing scientists to reconsider fundamental assumptions about what travels through the void between stars. The discovery story. Following the initial detection, astronomers rapidly organized international efforts to gather comprehensive observational data on 3Y Atlas during its brief passage through our solar system. Utilizing powerful instruments including the Hubble Space Telescope and sophisticated ground-based observatories, they systematically confirmed the object's size, composition, and increasingly unusual behavioral characteristics. The European Southern Observatory contributed crucial spectral data revealing complex surface features that appeared inconsistent with known cometary or asteroidal bodies. Dr. Michelle Bannister from the University of Canterbury discussed the significant challenges involved in imaging such a fast-moving, distant object while maintaining the precision required for detailed analysis. The collaborative international effort underscored both the urgency and scientific significance of capturing comprehensive models of 3 and Atlas during its fleeting passage through our cosmic neighborhood. Teams worked around the clock to coordinate observations across multiple time zones and hemispheres. The unprecedented level of cooperation demonstrated the scientific community's recognition that this visitor represented something truly extraordinary. Each new observation added pieces to a puzzle that seemed to defy conventional understanding of interstellar objects and their expected properties. A stranger in our midst. 3I Atlas exhibits characteristics unlike any object previously observed in our solar system or beyond. Recent measurements indicate it possesses unusually high reflectivity and metallic surface characteristics that fundamentally defy typical comet or asteroid classifications used by astronomers. Dr. Alan Fitzsimmons from Queen's University Belfast analyzed extensive telescope data, highlighting the strange spectral signatures indicative of advanced materials, rather than natural rocky or icy compositions. Traveling at nearly 60 kilometers per second, the object exhibits unexpected trajectory modifications that some researchers interpret as evidence of artificial propulsion systems. These remarkable anomalies have led a growing number of scientists to propose that 3Y Atlas may represent a technological artifact, possibly an extraterrestrial probe deliberately sent to observe our planetary system. Continued observations aim to definitively determine whether its behaviors represent unknown natural phenomena or constitute evidence of intelligent design and construction. The object's surface appears remarkably smooth and uniform, lacking the typical irregular features expected from natural cosmic debris. Its thermal emissions follow patterns that suggest internal heat sources rather than simple solar heating. These discoveries have fundamentally challenged existing models of what interstellar objects should look like and how they should behave. The predecessors. The previous two confirmed interstellar visitors, known as 1I/Oumuamua discovered back in 2017, and 2I/Borisov detected in 2019, provide crucial context for understanding 3I/Atlas. Yet, none of these objects actually share its peculiar characteristics. Oumuamua, for instance, initially baffled scientists with its really unusual cigar-like shape and that completely unexplained non-gravitational acceleration, which honestly just defied conventional physics. In stark contrast, 2I/Borisov displayed classic cometary behavior, showing typical outgassing patterns and developing a visible tail, just as you'd expect from natural objects. 3I/Atlas, though, with its massive size and highly reflective surface properties, fundamentally challenges the notion that interstellar objects always conform to previously known natural archetypes. The growing dataset from these three dramatically different visitors is systematically reshaping our understanding of what might actually be actively traversing our galaxy. Each visitor has contributed unique insights while, at the same time, raising increasingly complex questions about the diversity of objects traveling between star systems. The progression from Oumuamua's mysteries to 3I/Atlas's apparent technological signatures really suggests an escalating complexity that, well, demands serious reconsideration of our assumptions about interstellar space and its contents. The Cosmic Journey. The cosmic journey undertaken by 3I/Atlas spans potentially billions of years, originating from some unknown star system located far beyond the boundaries of our solar neighborhood. Dr. Davide Farnochia from NASA's Jet Propulsion Laboratory explains that the object's estimated age and remarkable velocity suggest it has successfully survived countless cosmic events, stellar encounters, and gravitational interactions during its extended voyage. Its calculated trajectory indicates a passage through the harsh environment of interstellar space for, potentially over 1 billion years, making it an ancient relic from the early epochs of galactic formation. Sophisticated spacecraft instruments have detected faint emissions, possibly linked to its primordial origin, which offers researchers a unique observational window into materials and processes from beyond our solar system. Understanding this extraordinary journey provides crucial insights into the fundamental processes shaping galactic evolution and the distribution of matter throughout cosmic history. The object's apparent structural integrity after such an immense voyage raises some pretty profound questions about its composition and construction. Natural objects typically show significant degradation after extended exposure to cosmic radiation and micrometeorite bombardment, yet 3I/Atlas appears honestly remarkably well preserved. A scientific goldmine. The discovery of 3I/Atlas represents without a doubt an unprecedented scientific opportunity, with an international array of telescopes and observatories now focused on capturing every possible detail during its passage. Scientific teams from NASA, ESA, and numerous other agencies are collaborating intensively to analyze spectral data, refine orbital models, and systematically search for evidence of non-natural phenomena. Dr. Sarah Seeger from the Massachusetts Institute of Technology emphasizes the extraordinary opportunities this visitor presents for studying interstellar chemistry, exotic materials, and potential technological signatures. The comprehensive data collection effort could, potentially unlock fundamental secrets about planetary formation processes in distant star systems and provide insights into the prevalence of advanced technology beyond our solar system. Each observation is carefully coordinated and scheduled to maximize scientific return during the object's limited time within optimal viewing range. The international cooperation on this project demonstrates unprecedented levels of coordination among research institutions that are typically quite competitive. Advanced imaging techniques are revealing surface details that really challenge our conventional understanding of natural space objects. Spectroscopic analysis has detected unusual emission lines that don't match any known natural materials, fueling speculation about artificial construction and exotic engineering materials. Unanswered questions. Despite extensive international study efforts, fundamental questions about 3I/Atlas remain frustratingly unanswered, leaving scientists divided about its true nature. Dr. Avi Loeb of Harvard University points out that certain observed behaviors definitely defy all known natural processes, including, unexplained acceleration patterns and highly unusual surface reflectivity characteristics. The object's true internal composition, structural configuration, and ultimate origin remain completely elusive despite intensive investigation. Competing hypotheses range from exotic natural cometary remnants to sophisticated artificial probes, potentially sent by extraterrestrial intelligence for reconnaissance purposes. Ongoing research efforts focus intensively on resolving these mounting mysteries, bolstered by significant advances in instrumentation and increasingly sophisticated observational techniques. The international scientific community remains fundamentally divided, carefully balancing healthy skepticism with genuinely open-minded inquiry as new data continues emerging. Some researchers argue for natural explanations involving unknown physics or exotic materials, while others increasingly favor artificial origin theories. The lack of definitive answers has created intense debates within astronomy journals and conferences. Each new observation seems to deepen rather than resolve the central mystery surrounding this enigmatic visitor from interstellar space. The alien question. The possibility that 3I/Atlas represents alien technology has moved from fringe speculation to serious scientific consideration among mainstream researchers studying its anomalous properties. Evidence supporting artificial origin theories includes the object's unusual mathematical heat emission patterns, sophisticated trajectory adjustments, and surface materials that appear inconsistent with natural formation processes. Dr. Seth Shostak from the SETI Institute reports that thermal emissions follow prime number sequences that are extremely unlikely to arise naturally and may represent deliberate signals or encoded information. This finding significantly strengthens the possibility that the object functions as part of a broader network of interstellar probes, communicating through universal mathematical codes that any technological civilization would recognize. The hypothesis suggests systematic interstellar exploration conducted by advanced civilizations using sophisticated reconnaissance technology designed to remain undetected until closely observed. Understanding these potential signals could fundamentally transform our approach to searching for extraterrestrial intelligence and establish first contact protocols. The implications extend far beyond academic interest, potentially representing humanity's first confirmed encounter with technology from another world. Such a discovery would necessitate careful consideration of response protocols and international cooperation in managing potential contact scenarios. Observing the visitor. The global astronomical community has mobilized unprecedented resources to observe 3I/Atlas, coordinating space-based telescopes, ground observatories, and advanced detection systems worldwide. Dr. Nancy Grace Roman's space telescope operations have been specially configured to track the object's trajectory and capture high-resolution images during optimal viewing windows. The Vera Rubin Observatory contributes continuous monitoring capabilities, while radio telescope arrays search for potential technological emissions or communication signals. Dr. Michelle Bannister from the University of Canterbury coordinates international observation schedules to ensure maximum coverage as the object traverses different regions of sky visibility. Advanced spectroscopic analysis reveals surface features that appear artificially smooth and uniform, lacking the typical irregularities expected from natural cosmic debris shaped by millions of years of space weathering. Thermal imaging detects internal heat sources that suggest active systems rather than passive solar heating patterns typical of natural objects. The coordination represents the largest international scientific collaboration in astronomical history, with researchers sharing data in real time across continents. Each observation window provides crucial data that may determine whether humanity faces a natural phenomenon or evidence of extraterrestrial technology visiting our solar system. Dawn of a new era. The implications of 3I/Atlas extend far beyond simple astronomical curiosity, potentially marking the dawn of a new era in humanity's understanding of our cosmic environment. Dr. Michio Kaku from City College of New York suggests that whether this object proves natural or artificial, it fundamentally challenges our assumptions about life, intelligence, and technology in the universe. The systematic study of 3I/Atlas has already driven innovations in observational technology, international cooperation protocols, and theoretical frameworks for understanding interstellar phenomena. These technological and methodological advances position humanity to better detect, analyze, and potentially interact with future cosmic visitors. The growing frequency of interstellar object detections suggests we may be entering an era of regular contact with materials and possibly intelligence from beyond our solar system. Future missions may attempt direct rendezvous with similar objects to conduct detailed analysis impossible from Earth-based observations. The scientific community recognizes that 3I/Atlas represents either an extraordinary natural phenomenon or humanity's first confirmed encounter with extraterrestrial technology. Either conclusion would fundamentally alter our understanding of our place in the cosmos and our readiness to engage with a potentially populated galaxy. The ongoing study of 3I/Atlas continues to challenge everything we thought we knew about interstellar visitors and our place in the cosmic community. Whether this mysterious object represents advanced alien technology or an exotic natural phenomenon, its discovery has already transformed our approach to studying the universe around us. As observations continue and data accumulates, humanity stands at the threshold of potentially world-changing revelations. Stay with Stellar Tech for continued coverage of this developing story that may forever change our understanding of life beyond Earth. What if the Big Bang wasn't the beginning but a rebirth? What if our entire 93 billion light-year observable universe is just a single object inside a much larger, older cosmos? This isn't science fiction, it's a possibility being explored by theoretical physicists, challenging our most fundamental understanding of existence. The clues might be hidden in plain sight, in the behavior of black holes and the baffling arrangement of the most distant galaxies spotted by the JWST. Let's explore this mind-bending possibility together. The standard Big Bang model. So, how did we arrive at our current picture of the universe? The story most of us know is the standard model of cosmology, first mathematically conceptualized by the Belgian priest and physicist Georges Lemaitre in 1927. It states that our universe exploded into being 13.8 billion years ago from a point of extreme density. From this intensely hot state, space itself began to expand. Over billions of years, gravity sculpted this expanding cosmos, pulling matter together to form the vast, web-like structure of galaxies we observe today. This model is incredibly successful. It explains the faint afterglow of the Big Bang, the cosmic microwave background, and it accounts for the accelerating expansion of the universe. This acceleration, confirmed in 1998, is often attributed to dark energy, which makes up about 68% of the universe. When combined with dark matter, at around 27%, it appears 95% of our cosmos is made of stuff we can't see or understand. This means that all the stars, planets, and galaxies we can observe make up a mere 5% of reality. The bottom line is the standard model, for all its successes, leaves us with the biggest questions in science completely unanswered. The black hole universe theory. What if there's a more elegant explanation? One that doesn't require inventing new particles or mysterious forces. A radical alternative, championed by physicist Nikodem Poplawski, proposes that our universe was born inside a black hole within a much larger parent universe. This idea flips our perspective on cosmic origins entirely. Instead of a singularity appearing from nothing, the theory suggests a physical process, the gravitational collapse of matter in a parent universe. Think of it like a star many times the mass of our sun collapsing to form a black hole, but on a cosmic scale. In this model, what we perceive as the Big Bang was actually the moment our universe formed inside that parent black hole. This framework elegantly resolves the issue of what came before the Big Bang, as the parent universe provides a clear preceding state. This cyclical model redefines our cosmic address, demoting our entire universe from everything that is to just one bubble in a potentially infinite cosmic foam. It also provides a physical source for the energy and matter in our universe, sourcing it directly from a pre-existing parent cosmos. In essence, the matter that makes up you, me, and the stars didn't appear from nothing, but was recycled from a previous cosmic iteration. Quantum mechanics and degeneracy pressure. Here's where things get really interesting, and it hinges on a core principle of quantum mechanics. Have you ever wondered what stops a dead star from collapsing forever? The answer lies in a rule established by the brilliant Austrian physicist Wolfgang Pauli. His exclusion principle states that identical particles, like electrons, cannot occupy the exact same quantum state at the same time. When gravity tries to crush matter into an incredibly small space, this principle creates a powerful outward push known as degeneracy pressure. The more you squeeze, the harder the particles push back. This is the force that supports white dwarfs against collapse, where matter is packed to a density of over 1 million kilograms per cubic centimeter. In even more extreme objects like neutron stars, the pressure is even greater, holding up against densities of over 100 trillion kilograms per cubic centimeter. This pressure is fundamentally different from thermal pressure, which supports a star like our Sun, as it doesn't depend on temperature at all. Proponents of the black hole universe theory argue that this same quantum pressure could operate on the scale of an entire collapsing universe, offering a mechanism to avoid the infinite singularity. The bounce mechanism. So, if a universe collapses, what happens when this quantum pressure kicks in? Instead of crushing down to an infinite point, a singularity where physics breaks down, the collapse could halt and rebound. This is the Big Bounce, a concept heavily explored in loop quantum cosmology by physicists like Martin Bojewald. In this scenario, as the matter of a parent universe collapses, it approaches the theoretical maximum density allowed by physics, known as the Planck density, which is about 5.1 times 10 to the 96th kilograms per cubic meter. At this point, quantum gravity effects become so powerful they overwhelm everything else. This force stops the collapse in its tracks and triggers a massive, explosive rebound. This rebound event would be incredibly brief but unfathomably violent, essentially resetting the cosmic clock for the new universe. To any observer inside this newly expanding region, that rebound would look and feel exactly like a Big Bang, while potentially preserving information from the prior cosmic cycle. This bounce also offers a potential solution to the black hole information loss paradox, a major conflict between general relativity and quantum mechanics. The paradox questions what happens to the information about matter that falls into a black hole if the black hole evaporates. A bounce mechanism suggests this information isn't destroyed, but is instead carried through the rebound event into the new universe, preserving the fundamental laws of physics. Evidence from early galaxies. This might all sound like fascinating speculation, but where's the evidence? It might be hiding in the deepest images of our universe captured by the James Webb Space Telescope. According to the Standard Model, galaxies should build up gradually. Yet JWST is finding galaxies that are bafflingly massive and mature. For instance, the GLASS JWST Early Release Science Program, involving astronomers like Rohan Naidu, has identified galaxies like GLASS Z12 at a redshift of 12, meaning we see them as they were just 350 million years after the Big Bang. These galaxies are already 1 billion times the mass of our Sun, far larger than our models predicted was possible so early on. Furthermore, these ancient galaxies appear to host supermassive black holes that are millions of times the Sun's mass, a phenomenon that standard models struggle to explain so soon after the Big Bang. The Big Bounce model, however, offers a potential explanation, suggesting these black holes could be relics that survived from the previous cosmic era, acting as gravitational seeds. Galaxy rotation mystery. Now for another cosmic puzzle that might point to the same conclusion. In a random and uniform universe, you would expect galaxies to be spinning in all different directions, with a roughly 50-50 split between clockwise and counterclockwise rotations. But that's not what we see. A 2020 study analyzing over 200,000 spiral galaxies, led by computational astronomer Lior Shamir, found a significant imbalance. There appears to be a preferred direction of spin, and alignment across vast stretches of the cosmos. The statistical probability of this asymmetry happening by chance is less than 1 in a billion. This unexpected alignment, observed across a scale of billions of light-years, implies that processes during the formation of the universe were not as random as we thought. This large-scale pattern challenges the long-held assumption that the universe is the same in all directions, a principle that underpins virtually all of our cosmological calculations. This isn't a small, localized effect. The pattern of this cosmic spin is coherent across billions of light-years. Shamir's analysis shows the distribution of spin directions fits a dipolar pattern, meaning it has a distinct north and south pole just like a spinning magnet or planet. Such a large-scale coherent structure is extremely difficult to generate after the Big Bang and points instead to a fundamental property imprinted on the universe at its very creation. Schwarzschild cosmology. So, this idea of a universe inside a black hole isn't, entirely new. It actually falls under a concept known as Schwarzschild cosmology. The name comes from Karl Schwarzschild, who, way back in 1916, found the first exact solution to Einstein's field equations, describing the space-time around a spherical mass, what we now call a black hole. The model suggests that the observable universe is the interior of a black hole existing within a larger parent universe. From our perspective, the Big Bang was the formation of this black hole, and from the outside, our entire cosmos would just look like a regular black hole. The size of this black hole's event horizon is defined by the Schwarzschild radius, and for a universe with the mass of ours, this radius is, interestingly, remarkably close to the radius of our observable universe. Mathematically, the singularity at the beginning of our universe is similar to the singularity at the center of a Schwarzschild black hole. The edge of our observable universe, a sphere with a diameter of 93 billion light-years, acts much like a black hole's event horizon, a boundary from which light cannot escape to an outside observer. Black holes as universe creators. Let's take this idea to its logical conclusion. If our universe was born inside a black hole, what does that imply about the estimated 100 million stellar mass black holes in our own galaxy? It suggests that each and every one could be a gateway, a seed for a new baby universe. This paints a picture of a vast cosmic ecosystem, a multiverse where universes are constantly being born. This concept, known as cosmic natural selection and explored by physicist Lee Smolin, could even offer an explanation for the fine-tuning problem, the mystery of why the fundamental constants of physics are so perfectly set for life. If universes are constantly being created, then perhaps only those whose physical laws allow for the creation of stable black holes can themselves reproduce, leading to a multiverse dominated by life-friendly universes. This theory proposes that our universe is so adept at creating black holes precisely because it was born from one, continuing an unending cosmic lineage. Smolin's theory suggests that the physical constants, like the strength of gravity or the mass of an electron, could slightly mutate with each new universe born from a bounce. Universes with constants that are better at producing black holes will have more offspring, and over countless generations these properties will become dominant. This makes the fine-tuning of our universe for life not a lucky accident but a predictable outcome of cosmic evolution on an unimaginable scale. Torsion and space-time twisting. For a universe to bounce instead of collapsing into a singularity, you need a powerful repulsive force at extreme densities. One candidate for this force comes from an extension of general relativity known as Einstein-Cartan theory. The mathematics behind this were developed in the 1920s by the brilliant French mathematician Élie Cartan. This theory incorporates a property of space-time called torsion, which accounts for the intrinsic spin of fundamental particles. This spin is a fundamental quantum property like mass or charge that gives particles an inherent angular momentum. In standard general relativity, space-time can bend, but it cannot twist, making the inclusion of torsion a significant modification needed for this theory to work. According to physicists like Nikodem Poplawski, at the densities found inside a black hole, the interaction between torsion and the spin of particles would create a powerful repulsive force. This torsion-induced bounce would be the mechanism that creates a new universe inside every black hole, making them not just cosmic destroyers but creators. Cosmic anisotropy. The evidence for a preferred direction in galaxy spins points to a concept called cosmic anisotropy, the idea that the universe is not the same in all directions. This directly challenges the cosmological principle, a foundational assumption in modern cosmology. This isn't just about galaxy spins. Anomalies in the cosmic microwave background radiation, first noted in data from the WMAP satellite and later confirmed by the Planck satellite, also suggest a large-scale alignment. Physicist João Magueijo famously dubbed this the axis of evil because it aligned with our solar system's plane, a result so strange it had to be a mistake, except it kept showing up with a statistical probability of being random at less than 0.1%. These anomalies, once dismissed as statistical flukes or errors in measurement, are now forcing a re-evaluation of fundamental assumptions, which is exactly how science progresses. The cosmological principle of isotropy has been a cornerstone of cosmology for nearly a century, so challenging it is met with significant scientific skepticism. However, as observational data from projects like the Sloan Digital Sky Survey and the Planck satellite becomes more precise, these persistent anomalies are becoming harder to ignore. If the universe truly does have a preferred direction, it would force us to rewrite our most basic models, and would strongly imply an origin story that involves rotation, just as the black hole universe theory predicts. From the impossible galaxies seen by JWST to the mysterious alignment of galactic spins, we are faced with observations that don't quite fit our standard story of the cosmos. The idea that our universe is inside a black hole, born from a cosmic bounce, offers a potential framework to explain these anomalies without inventing new physics. It suggests we might be part of an endless cycle of creation. What do you think? Are we living inside a black hole? Let me know your thoughts in the comments below. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Stellar Tech. Imagine this. After 47 years drifting through the cosmic void, humanity's most distant messenger suddenly detects something that, honestly, shouldn't exist. NASA's Voyager 1, now 15 billion miles from Earth, has captured evidence of 305 mysterious objects moving in perfect formation through interstellar space. These aren't planets, asteroids, or comets, they're something else entirely, gliding through the darkness with purpose and precision that just, well, defies every law of physics we know. What Voyager discovered out there has left scientists questioning everything we thought we understood about the universe. The Lonely Pioneer's impossible discovery. Deep in the frozen emptiness between stars, a tiny machine no bigger than a small car continues its eternal journey through the cosmic dark. Voyager 1, launched when Star Wars first hit theaters in 1977, has become humanity's most distant ambassador, traveling over 15 billion miles from Earth into the mysterious realm of interstellar space. This ancient spacecraft, powered by decaying plutonium and running on 1970s technology with less computing power than a modern calculator, was never meant to survive this long. Its mission was simple: fly by Jupiter and Saturn, then fade into obscurity. Instead, it crossed into interstellar space in 2012, becoming the first human-made object to venture beyond our sun's protective influence. Communication with Voyager takes 22 hours each way, like having a conversation where every response takes nearly 2 full days. Yet despite these impossible distances and technological limitations, this remarkable machine continues whispering back to us across the stars, carrying its famous golden record message to any intelligence that might find it. But recently, Voyager detected something in the darkness that has changed everything we thought we knew about the space between stars. The first anomaly that changed everything. What started as a routine data transmission from Voyager 1 quickly became something that would shake the foundations of space science. Hidden within the endless stream of plasma readings and magnetic field measurements was a tiny anomaly, a faint reflection of light that seemed insignificant at first glance. Dr. Eliza Karna, one of the mission specialists who first noticed the reading, described it as like shouting into a canyon for decades and finally something shouts back. The signal was so subtle that NASA's Jet Propulsion Laboratory initially dismissed it as background noise, just another particle drifting randomly through the cosmic void. But then the object began to move in ways that caught everyone's attention. It didn't tumble chaotically like space debris or follow the predictable paths of natural objects. Instead, it curved and accelerated with what appeared to be deliberate control, gliding smoothly through space as if guided by intelligence. Systems analyst Carlo Romero observed that the object's movement was unlike anything natural, describing it as the kind of deliberate motion one might expect from a drone rather than a rock. In the physics of space, things don't move with purpose unless something is making them move that way. When natural laws break down. When natural laws break down, when something unusual appears in space, scientists follow a standard protocol. They systematically check every known possibility. Is it a distant moon, a new asteroid, a comet with an unusual orbit? One by one, the team at NASA worked through these familiar explanations, and one by one, each possibility crumbled away. This object defied every category. It wasn't a planet, far too small, not a comet either. There was no tail, no ice trail, no heat signature that would indicate sublimating materials. It didn't glow like a star, and gravitational lensing couldn't explain its behavior. Even space dust was ruled out because dust particles don't suddenly change direction mid-flight. Dr. Lucas Hang at the Jet Propulsion Laboratory ran simulation after simulation, trying to match the object's behavior to known physical models. What makes space objects predictable is physics. Everything moves according to established patterns and forces. But this object broke those rules entirely. Its path bent in ways that didn't match any known orbital mechanics, with no drift or decay that would be expected from natural phenomena. The team was forced to confront an uncomfortable truth. What they were seeing wasn't just unknown, it was unnatural. The twin confirmation that proved everything. Just as scientists were struggling to understand what Voyager 1 had detected, something extraordinary happened that, honestly, transformed speculation into undeniable reality. Voyager 2, traveling a completely different path millions of miles away, detected something eerily similar, the same magnetic fluctuations, the same pulse patterns, matching signal signatures that changed everything. This cross-confirmation was the turning point in the investigation. Two separate spacecraft using independent instruments in different regions of space had detected nearly identical phenomena. This ruled out any possibility of internal error, software glitches, or sensor malfunctions on Voyager 1. ESA analyst Merck Fontaine compared it to, quote, two lighthouses both catching a flash of something passing between them. The dual detection gave the anomaly weight and credibility that just couldn't be dismissed. This wasn't noise or equipment failure, it was a real, coordinated phenomenon happening in the space between stars. With this confirmation, NASA quietly triggered what's known as a Level 3 alert, a designation reserved only for phenomena that don't fit within current scientific understanding. The event was real, the mathematics were consistent, and the movement patterns appeared deliberate. Nobody knew what to make of it, but everyone knew it was significant. The formation that defied physics. When the team analyzed the complete telemetry logs, what they discovered honestly sent chills through the scientific community. This wasn't just one or two anomalies drifting through space. There were 305 objects, all moving together in perfect formation like a cosmic ballet choreographed by an unknown intelligence. Each object glided past Voyager 1 in what appeared to be a coordinated arc, smooth and precise in their movements. These weren't debris fragments scattered randomly through space. There were no heat signatures, no tails, no signs of decay typical of natural objects. Most striking of all, the readings showed rhythmic pulses echoing through the plasma waves, patterns that suggested engineering rather than chance. The 305 objects maintained their relative positions with impossible precision. In space, groups of objects naturally spread out over time due to gravitational influences and velocity differences. Yet these maintained formation like a flock of birds or a school of fish. Except this was happening in the vacuum of space where such coordinated movement shouldn't be possible without technology. The scale was particularly unsettling. A single anomalous object might be explained as instrument error, but 305 objects all displaying the same unnatural characteristics suggested something far more significant was happening in interstellar space. The language hidden in plasma waves. As scientists examined the data more closely, they discovered something that, honestly, challenged the very nature of what they were observing. The plasma wave pulses weren't random cosmic noise. They contained patterns of repetition that were steady, measured, and structured in ways that suggested communication or control systems. Dr. Serena Patel from Caltech observed that the patterns felt less like nature and more like a language or system. The signals had loops, sequences, and structures that hinted at complexity far beyond random electromagnetic interference. These objects weren't just passing by Voyager, they seemed to be broadcasting signals as if pinging, scanning, or communicating with each other. The implications were staggering. If these patterns represented some form of communication, it suggested the objects were part of a coordinated network, operating with shared purpose and intelligence. Some experts went further, with ESA's Eric Lousy suggesting this could be some sort of probe network, though he was quickly asked to stop speculating publicly. To confirm their readings weren't the result of equipment failure, the team activated one of Voyager's oldest backup systems, a telemetry channel unused since the 1990s. It confirmed everything. The signals, the paths, the formations were all real. Impossible propulsion beyond our understanding. The mystery deepened when Voyager's instruments revealed how these objects moved through space. There were no engine flares, no ion trails, no signs of any propulsion system that human science could recognize. Yet, Doppler shift measurements showed these objects accelerating rapidly, smoothly, and directionally through the cosmic void. Some were moving faster than anything humans have ever launched into space. According to the data, certain objects were traveling at speeds that exceeded the calculated escape velocity of the entire Milky Way galaxy. These weren't passive objects drifting through space, they were powered somehow, navigating with purpose and incredible velocity. Dr. Caleb Ramirez from MIT noted that, Well, they're not floating through space, they're navigating it. What worried him more was their calculated path. These objects deliberately avoided our solar system, passing by at a safe distance as if they had no interest in stopping or investigating our cosmic neighborhood. The propulsion method remained completely mysterious. Nothing in current technology could explain how these objects moved. They appeared to be manipulating space itself, creating waves or ripples in space-time that allowed them to glide forward without conventional thrust. It was as if they were using the medium of space itself for propulsion. Earth hears the cosmic whispers. While NASA focused on analyzing Voyager's data, something remarkable began happening on Earth. Amateur radio operators across the globe, hobbyists with backyard setups built from spare parts, started reporting strange activity in their equipment. They were detecting weak, irregular pulses that didn't match any known terrestrial source. At first, these reports seemed unrelated to Voyager's discoveries. Radio interference happens constantly, and most dismissed it as coincidence. But when the timestamps were compared, they aligned almost perfectly with the hours when Voyager recorded its most intense plasma anomalies. These weren't professional observatories or official deep space listening stations. Most setups were designed to catch meteor scatter, amateur satellites, or solar flare activity, yet somehow, they were detecting faint echoes of what Voyager had encountered billions of miles away. The signals weren't strong, but they had pattern and regularity, like ripples reflecting off invisible walls in Earth's ionosphere. This raised troubling questions. Was this electromagnetic bleed-through accidental, or was something deliberately testing Earth's listening capabilities? The uncertainty triggered quiet security measures as NASA began encrypting parts of its deep space communications, recognizing that if amateur enthusiasts could detect these fragments, so could others with more sophisticated equipment. The machine that changed itself. Perhaps the most unsettling development was what happened to Voyager 1 itself. After one of the magnetic pulses from the passing objects, the spacecraft began exhibiting behavior that was never programmed into its systems. Its guidance system, the attitude and articulation control system, started rerouting data through old unused pathways that hadn't been active in decades. This wasn't system failure, it was systematic reconfiguration. Voyager was reactivating memory segments untouched since the 1980s, rerouting telemetry in ways that defied its original programming. The spacecraft was still responding to commands and transmitting data, but it was also doing something entirely new. Engineers had to dig through dusty file cabinets at NASA's Jet Propulsion Laboratory, searching for 1970s assembly language code and handwritten notes in paper manuals. Every diagnostic test took 44 hours, 22 hours to send a command, 22 hours to receive a response. Yet despite their efforts to reset the system, the new behaviors persisted. What they discovered was both promising and terrifying. The machine was stable, the instruments were functioning, but Voyager had fundamentally changed. Whatever had caused this transformation, it wasn't internal decay or software corruption. Voyager had encountered something that altered its very nature, making it part of something larger than its original mission. The network beyond the stars. As analysis continued, scientists began to consider a possibility that challenged everything we thought we knew about our place in the universe. The structured signals, the quantum-like oscillations, the coordinated movement patterns, all suggested that Voyager hadn't just witnessed random events in deep space. It had encountered evidence of a vast communication network operating in the interstellar medium. The waveforms resembled quantum entanglement experiments conducted on Earth, the same signals researchers use to transmit information between particles separated by distance. If this interpretation was correct, Voyager had stumbled into a galactic communication system that had been operating for millennia, undetected until now. Voyager's analog design, free from the electromagnetic noise of modern digital systems, made it the perfect cosmic microphone. Its position beyond the solar system's interference allowed it to detect signals that would be impossible to observe from Earth. The spacecraft had become an accidental eavesdropper on conversations not meant for human ears. The implications are staggering. If these 305 objects were part of a larger network, it suggests that the galaxy contains communication infrastructure built by intelligences we've never encountered. Voyager may have crossed into something we haven't mapped, not just empty space, but an active data layer that's been running unnoticed throughout the cosmos. From a single anomaly to 305 coordinated objects moving through interstellar space, Voyager 1's discovery has shattered our understanding of the cosmic void. Whether these objects represent natural phenomena beyond our current physics, or evidence of intelligence operating on a galactic scale, one thing is certain: the universe is far stranger and more active than we ever imagined. As Voyager continues its eternal journey through the darkness, it carries with it the knowledge that we are not alone in the vast emptiness between stars. Thanks for watching Stellar Tech, and don't forget to subscribe for more cosmic revelations. It's difficult for us humans to fully comprehend the enormity of space. We're comfortable in our own cosmic neighborhood, the solar system, and are used to familiar faces like Jupiter, Mars, and of course Earth. But beyond the heliopause lies the cold oblivion of interstellar space. Only 3 confirmed objects have ever crossed this threshold into our domain. These were the famous Oumuamua in 2017, Borisov in 2019, and now 3I/Atlas in 2025, visitors that bring with them both scientific excitement and perhaps even a hint of cosmic fear about what else might be traveling between the stars. Beyond the heliopause, our interstellar visitors. The vast expanse beyond our solar system represents one of the most hostile environments imaginable. A realm where temperatures approach absolute zero, and the nearest stars are separated by trillions of miles of empty void. Yet occasionally, objects from these distant stellar nurseries complete journeys lasting millions of years to visit our cosmic neighborhood. Interstellar space begins beyond the heliopause, approximately 120 astronomical units from the Sun, where our star's solar wind can no longer push back against the interstellar medium. Dr. Alan Stern from the Southwest Research Institute describes this boundary as humanity's cosmic doorstep, beyond which lies the true wilderness of the galaxy. The detection of interstellar visitors requires objects to exhibit hyperbolic orbits, trajectories that prove they're not gravitationally bound to our Sun and must have originated elsewhere. NASA's definition requires orbital eccentricity greater than 1.0 and excess velocity that cannot be explained by gravitational acceleration from solar system bodies. These mathematical signatures distinguish true interstellar objects from long-period comets that merely appear to come from great distances. The rarity of such detections makes each visitor precious, windows into the composition and formation processes of distant planetary systems that we may never reach with conventional spacecraft. The third visitor, 3I/Atlas discovery. January 2, 2025 marked a historic day in astronomy when the Atlas asteroid survey detected an unusual object that would soon become our third confirmed interstellar visitor. Dr. Larry Deneau from the University of Hawaii was monitoring the automated detection systems when object A11PL3Z appeared in the survey data, moving at an extraordinary velocity that immediately flagged it as anomalous. Unlike typical asteroids that follow predictable elliptical orbits, this object displayed hyperbolic motion characteristic of visitors from interstellar space. Dr. Robert Warwick, the astronomer who discovered both Oumuamua and helped confirm Borisov, led the initial follow-up observations that confirmed the object's interstellar origin. The Minor Planet Center in Cambridge, Massachusetts coordinated rapid confirmation observations from telescopes worldwide, including the Canada-France-Hawaii Telescope and Gemini Observatory. Within 72 hours, enough orbital data had been collected to definitively prove that A11PL3Z was traveling too fast to be gravitationally bound to our solar system. The object's discovery represents a milestone in astronomical detection capabilities, the first interstellar visitor found by automated survey systems rather than manual observation. 3I/Atlas received its final designation after the International Astronomical Union confirmed its interstellar trajectory and cometary activity, making it officially the third known visitor from beyond our solar system. The Atlas Survey System. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, represents a revolutionary approach to sky surveillance, designed primarily to detect potentially hazardous asteroids, but proving equally capable of finding interstellar visitors. Dr. John Tonry from the University of Hawaii leads the project, which operates 4 telescopes across Hawaii and South Africa, continuously scanning the entire visible sky every 24 hours. Each ATLAS telescope uses a 0.5-meter mirror equipped with advanced CCD cameras, capable of detecting objects as faint as magnitude 19.5. The system processes approximately 100 terabytes of data monthly, using sophisticated algorithms to identify moving objects against the background of stars. ATLAS distinguishes itself through rapid cadence observations, taking multiple images of the same sky regions within hours to detect object motion. The discovery of 3I/ATLAS validated the system's ability to detect rare phenomena beyond its primary mission. Dr. Deneau noted that the automated nature of ATLAS allows us to catch objects that human observers might miss due to their subtle motion or unusual characteristics. The system's success has prompted NASA to fund expansion to additional sites, creating a global network capable of providing even earlier warnings for both hazardous asteroids and interstellar visitors that might otherwise escape detection. From A11PL3Z to C2025N1, the naming journey. The designation journey of 3I/ATLAS really illustrates the complex process astronomers use to classify and name celestial objects. So, initially it was designated A11PL3Z by the ATLAS survey system, but, as its true nature became apparent, the object underwent multiple reclassifications. Dr. Gareth Williams at the Minor Planet Center explained that automated survey systems use temporary alphanumeric codes before official designations are assigned. Once hyperbolic orbital motion was confirmed, the object received the provisional designation C/2025N1, which indicates a comet discovered in the first half of July 2025. The C/prefix denotes a non-periodic comet, while 2025N1 tells us it was the first comet found during the 14th half-month period of that year. As observations revealed clear cometary activity, including coma formation and tail development, the International Astronomical Union assigned the final designation 3I/ATLAS. The 3I prefix marks it as the third interstellar object, following 1I/Oumuamua and 2I/Borisov. The ATLAS portion honors the survey system that discovered it, following IAU traditions of crediting discoverers. This naming evolution really reflects the careful verification process required to confirm interstellar origin, ensuring that only objects with definitively hyperbolic orbits receive the prestigious EIN designation reserved for visitors from other star systems. A hyperbolic journey at 58 kilometers per second. 3I/ATLAS approaches our solar system with a hyperbolic excess velocity of 58 kilometers per second, a speed that definitively proves its interstellar origin and provides clues about its cosmic journey. Dr. Davide Farnochia from NASA's Jet Propulsion Laboratory calculated that this velocity places 3I/ATLAS among the fastest interstellar visitors ever detected, suggesting either a recent gravitational encounter with another star, or acceleration from its parent system. The object's trajectory indicates it entered our solar system from the direction of the constellation Lynx, possibly originating from the Vega stellar system, which is about 25 light-years away. Orbital mechanics reveal that 3I/ATLAS has been traveling through interstellar space for an estimated 1 to 3 million years before encountering our solar system's gravitational influence. The object's perihelion, its closest approach to the Sun, occurred on October 30, 2025, at a distance of 0.65 astronomical units, which is well within Earth's orbital radius. Dr. Alan Harris from the German Aerospace Center noted that this close solar approach provides optimal conditions for studying the object's composition through spectroscopic analysis and thermal emission observations. The hyperbolic nature of the orbit means 3I/ATLAS will never return. After its solar encounter, the object will be gravitationally accelerated by our Sun, eventually reaching speeds exceeding 70 kilometers per second as it exits toward the constellation Draco. Brightness, rotation, and the 29-hour cycle. Photometric observations of 3I/ATLAS have revealed a complex 29-hour rotation period that provides crucial insights into the object's shape, composition, and structural integrity. Dr. Alan Fitzsimmons from Queen's University Belfast leads the International Photometry Campaign, coordinating observations from telescopes worldwide to track the object's brightness variations over time. The 29-hour cycle shows magnitude variations of approximately 1.5, which indicates either a highly elongated shape similar to Oumuamua, or surface features with dramatically different reflectivity properties. Light curve analysis by Dr. Mikael Granvik from the University of Helsinki, suggests the object is likely tumbling rather than rotating around a single axis, which is consistent with an object that has experienced gravitational perturbations or impacts during its interstellar journey. The rotation period is significantly longer than typical solar system comets, which usually rotate every 6 to 12 hours due to outgassing torques. Thermal infrared observations using the Spitzer Space Telescope show that 3I/Atlas maintains surface temperatures consistent with its distance from the Sun, but with unusual temperature distribution patterns that suggest non-uniform surface composition. The object's brightness peaked at approximately magnitude 10 during perihelion, making it visible to experienced amateur astronomers using moderate-sized telescopes, but remaining too faint for naked-eye observation, despite its considerable size. Coma, tail, and cometary activity. Unlike the mysterious Oumuamua, 3I Atlas displays clear cometary activity which has, provided astronomers with valuable data about its composition and structure. Dr. Matthew Knight from the University of Maryland leads studies of the object's coma, the fuzzy atmosphere of gas and dust surrounding the nucleus as solar heating vaporizes surface materials. The coma began developing when 3Y Atlas reached approximately 2.5 astronomical units from the Sun, initially appearing as a faint envelope around the central nucleus. Spectroscopic analysis by Dr. Michael DeSanti from NASA Goddard Space Flight Center detected emissions from water vapor, carbon monoxide, and hydrogen cyanide, typical signatures of comet sublimation, but with unusual abundance ratios. The object developed a visible tail reaching lengths of 200,000 kilometers as it approached perihelion, composed primarily of dust particles ejected by outgassing. High-resolution imaging from the Hubble Space Telescope revealed the tail's structure shows periodic variations corresponding to the object's rotation, indicating active regions on the nucleus surface. Dr. Jacqueline Keene from Boston University noted that the gas production rate of 3Y Atlas is approximately 10 times higher than expected for its estimated size, suggesting either unusual composition or internal structure. The cometary activity confirms 3Y Atlas as a volatile-rich object that formed in the outer regions of another stellar system, where temperatures were low enough for water and other compounds to condense. Oumuamua versus Borisov versus 3I/Atlas. So let's compare these three confirmed interstellar visitors: Oumuamua, Borisov, and 3I/Atlas. They really present a fascinating study in contrasts, revealing just how diverse the objects traveling between stellar systems can be. Oumuamua, which was discovered by Dr. Robert Warwick back in 2017, is still the most enigmatic of the bunch. It showed no cometary activity, even when it got close to the Sun, and it had this unexplained acceleration and extreme elongation that made it, truly unique among known solar system objects. On the other hand, 2I Borisov, which was found by amateur astronomer Gennady Borisov in 2019, behaved exactly as astronomers expected an interstellar comet would. It developed a classic tail, showed predictable outgassing, and had a composition pretty similar to solar system comets. Then there's 3I Atlas, which represents something kind of in-between. It displayed clear cometary activity but with some unusual characteristics that set it apart from typical comets. Dr. Stefano Bagnulo from Queen's University Belfast led comparative studies showing that Borisov had carbon monoxide ratios similar to solar system comets, while 3Y Atlas showed significantly different volatile abundances. When it comes to size, estimates put Oumuamua at around 400 meters long, Borisov at roughly 1 kilometer in diameter, and 3Y Atlas at an estimated 5 to 10 kilometers across, making it potentially the largest interstellar visitor we've detected so far. All this suggests that Oumuamua might represent a rare class of objects, while Borisov and 3I Atlas indicate that typical interstellar comets actually share a lot of characteristics with their solar system cousins. A 3 billion 11-year-old traveler. Determining the age of 3I Atlas is, honestly, one of the most challenging aspects of studying interstellar objects. It requires some pretty sophisticated modeling of cosmic weathering processes and orbital dynamics. Dr. Grigory Fedorets from Queen's University Belfast estimated the object's age to be somewhere between 3 and 11 billion years, based on its surface spectroscopic properties, and assumed travel times from nearby stellar systems. That's pretty wild. It means 3I Atlas could be older than Earth itself, having formed during those early epochs of galactic evolution, when star formation rates were way higher than they are today. Now, cosmic ray exposure modeling by Dr. Renu Malhotra from the University of Arizona suggests the surface should show significant radiation damage after billions of years in interstellar space, but interestingly, observations indicate a surprisingly pristine composition. The age estimates assume 3I Atlas originated from stellar systems within 100 light-years of our current galactic position, though honestly the actual birthplace could be much farther away, given the complex orbital motions of stars over galactic timescales. Dr. Fatih Namouni from Côte d'Azur Observatory calculated that objects of this age could have originated from star-forming regions that no longer even exist, having been dispersed by galactic rotation and stellar evolution. The ancient nature of 3I Atlas gives us, well, a unique opportunity to study materials from the early solar system formation epoch, potentially preserving chemical signatures from primordial stellar nebulae that formed billions of years ago. October 30th, perihelion and beyond. October 30th, 2025 marked the closest approach of 3I Atlas to our Sun, giving astronomers around the world optimal conditions for detailed study of this ancient interstellar visitor. Perihelion observations coordinated by Dr. Casey Lise from Johns Hopkins Applied Physics Laboratory used, honestly, just about every major ground-based observatory and space telescope to capture as much scientific data as possible. The 0.65 AU closest approach placed 3I Atlas well within Earth's orbit, allowing for unprecedented resolution observations of an interstellar object's nucleus and its active regions. Solar heating during perihelion triggered peak cometary activity with gas production rates reaching 10 to the 28th molecules per second, and a tail stretching over 500,000 kilometers. Dr. Tony Farnham from the University of Maryland reported that high-resolution imaging revealed surface features and active jets similar to solar system comets, but, interestingly, with some unusual spatial distribution patterns. After perihelion, tracking shows that 3I Atlas will stay observable until about mid-2026 before fading beyond the detection limits of our current telescopes. The object's exit trajectory toward the Draco constellation has been calculated with precision, with a final velocity exceeding 75 kilometers per second as it leaves our solar system for good. Looking forward, future observations will focus on long-term monitoring of the tail's evolution and spectroscopic analysis of outgassing products, which will keep revealing secrets about interstellar comet formation and the chemical evolution of distant planetary systems. 3I Atlas has given astronomers an unprecedented opportunity to study pristine material from another star system, bridging billions of years and countless light-years to reach, well, our cosmic doorstep. This ancient traveler carries chemical signatures from stellar environments we may never visit, and its cometary activity proves that familiar processes are at work throughout the galaxy. As 3I Atlas continues its eternal journey beyond our solar system, it leaves behind invaluable data that expands our understanding of planetary formation all across the cosmos. Be sure to subscribe to Stellar Tech for more discoveries about our universe's most distant messengers.